You have watched an AI suddenly go from writing poetry to solving complex math problems and debugging code overnight. It never actually had a sudden breakthrough. That sharp turn in reasoning came from something else entirely. Someone trains it with reinforcement learning and flips a switch on its entire brain. Most creators overlook the real shift because the pre-trained model already knows how to talk. Reinforcement learning teaches it how to think. Imagine you train a dog to fetch a ball. You never code specific muscle movements to make it happen. You show it the ball and watch it bring you something back. You only reward that right behavior with a treat. It takes thousands of tries before it finally figures out what you want. Reinforcement learning for LLMs works the exact same way. The dog becomes a neural network, and the treats turn into numerical scores. First, the model generates an answer to your question or problem. A reward system evaluates how good that answer really is. Then you make the adjustment. The internal weights shift slightly to make high-scoring answers more likely next time. You repeat the whole loop until it locks in the skill. You run this loop thousands or millions of times. The real magic lives in the scoring system. Nail the right answer and the score goes positive, while a wrong pick turns it negative. Ramble when brevity works and that number drops. Miss the point entirely, and that score drops too. The model slowly learns the exact shape of what you actually want. It skips rote memorization and focuses entirely on discovering what delivers good results. You trained it on trillions of words pulled from the internet, books, articles, code, and forums. It quietly mapped the statistical patterns behind it all. Before RL kicks in, a large language model is just a highly trained autocomplete engine. Give it a few opening words and it will reliably guess what comes next with startling precision. Predicting the next word does not equal understanding. It is simply massive pattern matching. It can draft a flawless explanation of quantum mechanics while grasping absolutely zero concepts. The system is only chasing word sequences instead of reasoning about reality. Pre-training teaches a model to recognize patterns, but it lacks real judgment. Reinforcement learning fixes that by rewarding choices that actually make sense. Suddenly, the AI starts thinking ahead. The model stops guessing what comes next and starts working toward a clear target. We reward it only when the output hits that goal. Now it learns to aim instead of just finishing patterns. You get a tool that solves actual problems instead of just repeating what it heard. The leap is massive. One mimics while the other figures it out. Fine-tuning actually kicks off before reinforcement learning ever touches the model. You start by shaping its raw knowledge into a usable form. Only then does goal-driven training take over. You grab a finished base model and drill it on exact tasks or strict formats. The AI learns to match your style and follow precise instructions. Suddenly, it stops drifting and starts delivering exactly what you need. Pre-training hands the model a broad understanding of how language actually works. Fine-tuning then trains the model to step into specific roles like a chatbot or coding assistant. You feed it thousands of solid Q&A pairs and tweak the weights to mirror those patterns. Fine-tuning is supervised learning, where you pair each question with the exact answer, so the model learns to copy that style. It works exactly like showing a student a perfect answer and telling them to write like this. Reinforcement learning arrives right after fine-tuning. Fine-tuning teaches the model what to write, while RL grades whether those words actually land. Fine-tuning handles the manners. RL builds the judgment. We are skipping the equations and borrowing a kitchen analogy instead. Imagine teaching someone to cook. You would never hand them a thermodynamics textbook first. You let them cook and taste the result while calling it too salty or perfect. They build real intuition over time. The model cooks by generating text while the reward function tastes and scores each result. Does the math hold up? Is the reasoning actually sound? Is it actually helpful and honest? The chef adapts by adjusting internal weights to produce tastier outputs next time. Several approaches to this tasting phase have evolved significantly. RLHF stands for Reinforcement Learning from Human Feedback. Humans simply rank the model outputs from best to worst. Separate reward model studies those rankings. The main language model then trains to maximize that score. The original approach works beautifully because human judgment captures nuance that machines completely miss. Human raters cost a fortune and move too slow. Scaling them becomes a massive bottleneck. Enter RLVR, which stands for Reinforcement Learning from Verifiable Rewards. You skip human judges and use tasks with objectively verifiable answers. Newer reasoning models run on this exact system. It delivers faster, cheaper results and often beats human judgment because there is no room for error. Did the math check out and does the code pass every test? If the simulation hits the target, you reward it. If it fails, you penalize it. Human preferences are messy because subjectivity is baked into every choice. Skip training a reward model and skip reinforcement learning. DPO directly optimizes the language model using preference pairs. Direct preference optimization is a straight shortcut. It skips the entire reinforcement learning loop. You just feed it pairs that say this answer is better than that one. The goal stays the same with fewer moving parts and noticeably better stability. Think of it as cutting out the middleman to get straight to the result. It tweaks the model weights in tiny measured steps so it never forgets what it already knows. Think of it like adjusting a family recipe without ruining the signature dish. PPO, or Proximal Policy Optimization, serves as the workhorse reinforcement learning algorithm behind RLHF. It keeps the model learning without taking wild, risky leaps. GRPO, or Group Relative Policy Optimization, is a newer variant gaining traction. Teams are leaning on it to solve complex reasoning tasks with better stability. Andrej Karpathy mapped out the entire process in his famous diagrams. You see pre-training first, followed by supervised fine-tuning, and finally reinforcement learning. Here is the core insight worth remembering. Each stage brings something fundamentally different to the table. That is exactly why the whole pipeline works. Pre-training teaches language, while fine-tuning shapes behavior, and reinforcement learning drives quality. Today's headline-generating models are not just bigger or better pre-trained. They have passed through more sophisticated reinforcement learning cycles. Smarter reward signals now guide every decision. That shift makes them appear to reason rather than simply predict. This reasoning was never coded into the system. It grew organically through the training process itself. The biggest unanswered question right now is reward design. We still have to figure out how to build those systems. A poorly designed reward function makes a model game the system. It spits out confidently wrong answers. It inflates test scores or becomes completely evasive. The reward function is the single most impactful hyperparameter in RL training. Getting it right is brutally difficult. Fixing rewards means understanding what you actually want. You have to look past what is easy to measure. Most people assume AI just reads the internet and writes stuff. That misses the real process. There are 3 distinct training stages. The final stage is reinforcement learning. That is exactly what creates the breakthroughs you see today. We start with pre-training to teach raw language patterns from massive text dumps. This stage runs for months across thousands of GPUs. Next comes supervised fine-tuning, where we show labeled examples of helpful behavior. You only need a few days to lock in those responses. Then we layer on reinforcement learning to shape good outputs through trial and error scoring. That refinement takes anywhere from days to weeks. Step 1 makes the model fluent. Step 2 makes it helpful. Step 3 makes it smart. The trend is moving decisively toward verifiable rewards, or RLVR, over pure human feedback, or RLHF, for reasoning tasks. We do this because verifiable signals actually scale. Rewards scale infinitely and stay completely objective. Both approaches actually share one core idea. You reward the good stuff and penalize the bad while the model figures out the rest. Reinforcement learning builds the bridge between a model that just knows words and one that actually knows what you want. It is exactly why your AI assistant stopped acting like a parrot and finally started working like one. The models getting smarter are not picking up new facts. They are simply learning to use what they already know with far more reliability and precision. The next wave of breakthroughs will never come from bigger models or more data. They will come from better ways to reward the models that already exist. That is exactly what reinforcement learning gives them. What actually separates fine-tuning from reinforcement learning in LLM training? Reinforcement learning scores every output and adjusts the system without ever handing the correct answer up front. Fine-tuning uses supervised learning to directly teach the model exactly how to behave. Fine-tuning shows the student model answers up front. Reinforcement learning grades the work and demands a better try. What exactly is RLVR, and how does it differ from RLHF? RLVR stands for Reinforcement Learning from Verifiable Rewards and targets tasks with objective answers like math code execution or simulations. It runs faster and cheaper while scaling better by dropping human judgment and removing subjectivity entirely. Traditional RLHF expands to reinforcement learning from human feedback and relies completely on raters scoring outputs and ranking responses. Why does the reward function rule reinforcement learning? It dictates every single training step. Mess with the reward and the model will instantly game the system. It will spit out confidently wrong answers just to hit high scores. The model only cares about one thing. It optimizes exactly for what you reward and absolutely nothing else. That is why metrics easily trump actual quality. A sharp reward function aligns the model with your real goals. Precision here is everything. Get this right, and you control the entire pipeline. It is the single most impactful design decision in all of reinforcement learning. That's the full picture. If this made it click, tap subscribe. There's a new AI explainer here every day, and tap the video on screen to keep going. See you in the next one.